For number 11, we've got a battery connected to a resistor and a parallel plate capacitor, and we want to determine the energy in the capacitor when the switch is closed for a long time. If this is 18 volts, then over a long time this is also going to be 18 volts, and our energy equation for capacitors is 1/2 CV squared, which is 1/2 9 times 10 to the negative 6 times 18 squared. So that gives us 0.00146 joules. So how much work is done to increase the spacing between the plates? The spacing increased by 3 times its original. Here's our equation for the capacitance of a capacitor. And since the distance is increasing, the capacitance has to decrease. And so C nu is equal to C naught over 3. And then it says the change time took time negligible, meaning a very short period of time. Over a very short period of time, this is our other equation for capacitance, charge over voltage. The capacitance changes. The voltage needs a long period of time to build up the original voltage that it had. So the voltage is going to change while the charge, which hasn't had time to move yet, is going to stay the same. So the capacitance and the voltage are inverse proportions. So the voltage is going to increase, and the new voltage, Vn, is going to be 3 times the original voltage. So how much work is done increasing the spacing? Work is based on change in energy. So change in energy is U final minus U initial. So let's work with variables first. We'll plug in values later. U initial is just 1/2 C naught V naught squared. U final is 1/2 C naught over 3 times 3 V naught squared. If I narrow this down, I get 3 times 1/2 C naught V naught squared, which means I really have 3 times the original, I'll call this O, original energy. So my change in energy, or my work, is 3 U naught minus U naught, which is 2 original energy, and that gives me 2 times 0.00146 joules I got in part A. Work here is 0.00192 joules. Determine the current in the resistor immediately after the spacing is increased. So we're going to use the current is voltage over resistance. Our voltage, we established in part B, increased by 3 times the original, and the resistance stays the same. So we're going to plug in the values of 36 volts over 1.2 times 10 to the 5 ohms, and that gives me 3 times 10 to the negative 4 amps. After a long time, the circuit reaches a new static equilibrium, and determine the total charge that passes through the battery. So after a long time, our voltage goes back to the original voltage that it started with. And then the charge that passes through the battery, if we have, we would need to figure out the change in charge, which is Q final minus Q initial. Our Q final is equal to the charge times voltage, which we established decreased by 3, and the voltage after a long period of time goes back to the original voltage of 18. So that gives us 6 times the capacitance value, which is 5.4 times 10 to the negative 5. And this is the original capacitance, right? So that's in coulombs. And then Q initial is going to be the capacitor after it is changed, but initially the voltage was 54 volts. So that was 3 times the voltage that it had originally, and so that gives me 18 times the original capacitor. The answer to this one is 1.62 to the negative 4 coulombs. And then the change in charge is going to be Q final minus Q initial. That's going to give me the 1.08 times 10 to the negative 4 coulombs. So this is your total charge that passes through the battery. And then determine the energy added to the battery. So the last step for part E is to determine the energy added to the battery. We know that 1.08 times 10 to the negative 4 coulombs have now passed through the battery, have entered the battery. That's the extra amount of coulombs. And so we have the energy equation. Let me go backward. The energy equation, when we're working with general electrical energy, is voltage times charge. Our voltage is the voltage of the battery, and then the extra charge that goes into that battery, which is equal to 0.00194 joules.